shot will take up, we're looking at the potential flow of irrotational past a cylinder we work at the cylindrical coordinate system. The origin is fixed like this, and this is the x-axis, and this is the y-axis, and we assume that the fluid far away from the cylinder has a velocity given by v infinity in the x direction. What we are interested is in the velocity profile at regions close to the cylinder. So we are again considering an incompressible fluid. So the incompressible fluid, the continuity equation is the divergence of the velocity vector field is 0. And further, if I introduce the fact that it's an irrotational fluid, which means that the velocity can be expressed as the gradient of a potential. So V is equal to minus potential, which we will find. So what we are doing is not finding the velocity directly, but finding the potential and using this equation to find the velocity. So if I substitute this here, then I get that the Laplacian of phi is C. So phi satisfies the Laplacian equation. So Laplacian in cylindrical coordinates we can easily get from the tables. So here we are assuming that V is actually considering a sort of a two-dimensional flow. So V is given by V RC E RC plus V phi E phi. So we are neglecting the Z component of the velocity profile. But I haven't, it's a two-dimensional case of the Laplacian that we will consider. Okay. So in these two dimensions, the Laplacian would be 1 over RC d by d RC and sorry. Phi by dRc plus 1 over RC squared d squared phi by d phi squared is c. That is the, this phi is the potential. The cylindrical coordinate phi is given by different phi. So I hope you can see the difference. This is the equation satisfied by the Laplacian. Clearly it's a linear equation, and you would expect that this can be solved by the separation of variables. Right? So I can look for a solution of the form phi RC phi, some function of RC times some function of G. So you can do the standard operations. So this could lead to, what could this lead? Right? So d phi by dRc is simply f prime of RC times G of phi. Right? So RC times that would be RC times this. And then I have to again differentiate d by dRc of this is d of phi can be taken out. So I will have to differentiate this with respect to RC. So this would be RC times f double prime of RC. But the prime here stands for derivative with respect to RC of the function f. That's clear from the context. Plus f prime of RC. That is there. So 1 over that times d of phi times RC f double prime of RC plus f prime of RC plus 1 over RC square d square phi by d phi square. So that would be f of RC times d square t by d phi square. So I just write it explicitly. F of RC times d square t by d phi square is equal to 0. We should be able to separate this. If I multiply 2 by RC square by f of RC d of phi divide by f of RC and d of phi. So this would be, if I can first start. So I will take that in, and then now I have to multiply by RC square and divide by f of RC. So this would be f double prime of RC by f of RC square. And so I am multiplying both the equation by RC square and dividing by f of RC and d of phi. Term by term I am doing. So divide by d of phi, this would vanish. Divide by f of RC, I get this. Multiply by RC square. Then plus RC, f prime of RC. Right? Divided by f of RC. So then is equal to minus d square g by d phi square d of phi. That's what I will get. Right? So this is what I will get. So clearly, this is a function of RC alone. This is a function of phi alone. So I can equate it knowing that I am getting something similar to an eigenvalue problem. I simply call it lambda, some constant. Right? So if I now join these two, this portion, then I get d square g by d phi square is equal to plus lambda t of phi is equal to 0. Now, you can consider all possible cases, but finally it's possible to show that only the case lambda greater than 0 would lead to the solution. So I will leave it for you to check what would happen for lambda equals 0 and less than 0 and verify that you probably only get the trivial solution in those cases. Right? So I am going to consider only the case where lambda is greater than 0. Typically that's what you would do. Maybe more generally possibly, but of course you need also the boundary conditions to show that the eigenvalues for this problem would be real and positive. You should be able to show it in general. If you are not able to do that, just have to try all the three possible cases. And clearly we expect lambda to be real, right? Because otherwise we are going to get an equation with complex coefficients. So lambda is real. We don't know whether it's positive, 0 or negative. So we have to try typically all the three cases and verify what we will get in each case. So I'm going to let you try the case for lambda equals 0 and less than 0. I'm going to consider only the case where lambda is greater than 0. In that case, the characteristic equation for that would be m squared plus lambda equals 0. So the roots of the characteristic equation will be complex. So I can write that d of phi is some combination of cosine and sine function. So d of phi can be written for the case of lambda greater than 0. Right? Clearly where the roots are complex. Right? When I say root of lambda, take the positive value of the root. So it would be I times that. And for this case, the general solution will be of the form. I can put this as some constant, let's say some C1 cos lambda phi plus C2 sin. So this is the form it would have. Now let's look at what would happen to the F equation. So we have to combine the two and then based on the boundary conditions find the solution. The boundary conditions are there for the velocity, right? We'll go step by step for some reason. I won't discuss the boundary conditions now, but first let's solve for F, right? So now I get RC square F W B squared, let's write it explicitly, plus RC F by BRC, and then I get F of RC, right? So minus lambda times F of RC is equal to 0. This is again another standard case of what Stewart would like to call the equidimensional equation. So what I want to point out clearly in the exam, I expect you have enough background to write at least the solution for these simple cases. At least those which we have encountered in the course. You should know how to construct the solution. This is not about mathematical methods, but you cannot claim complete innocence of anything related to mathematics. Right? In case you haven't encountered, at least in this course, I will give you a hint. For instance, in many cases, we simply assume that the angular dependence will perform sin square theta, cos square theta, whatever. In those cases, I give you those hints. Otherwise, but given the hint, you should be able to construct the solution. So this is the type of equation which we have encountered many times. So you should know without any hint from me that we are supposed to seek a solution of the form, let's say A R power n, and then we have to find n, right, by substituting. So that's all. So this would be ARC. So this would be RC square times n into n minus 1, right? RC power n minus 2 plus RC times n into RC power n minus 1 minus lambda. Well, this won't even consider the A because that's going to get cancelled out. RC power n is equal to 0. So we get n into n minus 1 plus n minus lambda equal to 0, and so we get n squared is actually equal to lambda. So since lambda is, I'm considering only the case where lambda is greater than 0, clearly n is equal to plus or minus root lambda. So what would be the solution of f of RC would be some, I can put it as d1. Yeah, RC raised to root lambda plus d2 RC raised to minus root lambda. Right, so that's what I would have. Now, first, so there are now the solution itself now can be written as d1 RC root lambda plus d2 RC minus root lambda times c1 cos root lambda phi plus c2 sin root lambda phi. So I'm discussing this solution in some detail. It belongs to separation of variables, you should be able to do it by yourself, but we might encounter these repeatedly when we come to solving stream function equations or potential flow equations. So if you've gone through once, then you should be, most of the solutions turn out to be very similar, right? At least an approach. So now we have to look at, first of all, we haven't even found what the lambda is. That problem hasn't been solved, and on top of it, we seem to have 4 constants. It seems too much of a problem, but they will see that some of these constants can be combined when we apply the boundary conditions. Let's now look at the boundary conditions. So we erase this middle portion and then look at the boundary conditions. So as we have seen in the case of the flow past the sphere, there are 2 types of boundary conditions. One which deals with the arc or large distance boundary condition. So that is always convenient to apply that first before we come to what is happening on the surface of the cylinder. Right? So let's look at what the limit RC going to infinity of B is B infinity times Ex. That's how we have constructed the coordinate system, so that this is what I have. But what we want though are boundary conditions expressed first in terms of BRC and B phi, right? And then we have to convert that to conditions on the potential function, something very similar to what we follow to find the stream function for the flow past the sphere, right? So this would mean that limit RC going to infinity of BRC is simply B infinity Ex dotted with ERC. That's the simplest way to proceed, right? So what is ERC dotted with Ex? Can you tell me? Because I don't have it with me here. Cos phi or minus cos phi or the other is for ERC, how it is expressed in terms of Ex. Cos phi, right? So cos phi Ex. Then this is okay, that we might not need it. So this is kB infinity cos phi, and probably my guess is the other one would be minus sin phi. Is it minus B infinity sin phi? Right? So you have to confirm that. Is that correct? What I am asking is what is Ex dotted with E phi? Minus sin phi. This is what we have. So we have applied the condition. Now, what we have is, so since B is given by this, and so we need to know what the gradient is in. So BRC ERC plus B phi E phi is equal to minus the gradient of the potential. So that would be minus ERC D by ERC phi plus 1 over RC D phi, the potential, divided by, the derivative with respect to the cylindrical coordinate phi, E phi. So clearly, BRC is minus B phi by BRC, and B phi is minus 1 over RC. So you will find again that either you apply this or this, you will get the same set of equations for the constant. So I'm going to take this because it seems to be easier to differentiate phi, right? So I will leave it as an exercise for you to work on this, right? So let's apply this, right? So what I have is limit RC equal to infinity B phi, which is equal to minus B infinity sin phi. This is limit RC equal to infinity. So actually limit RC equal to infinity of B phi is actually right property. So RC by d phi is equal actually to minus d infinity sin phi, so which implies that limit rc going to infinity 1 over rc d phi by d phi is, I didn't do it. d phi sin d infinity sin phi, right? So this is what I have. So let's take this and then we equate to d infinity sin phi. Limit rc going to infinity 1 over rc, and then I have d1 rc lambda plus d2 rc minus lambda times, I have to now differentiate that with respect to phi. So that would be minus lambda c1 sin plus c2 lambda cos. So you can see that we need to get sin phi here. So you can expect that lambda is going to turn out to be 1. Actually, interestingly, in this case, the only possible solution to the eigenvalue problem is lambda greater than 0, of course, but it will turn out that lambda is actually equal to 1. That can be easily guessed by looking at what this has to be equated. But if you look at this, and if you want to look at and see what will happen to this, because this is where all the RC terms are, you're getting RC going to infinity, so one has to be very careful, and I don't know what lambda is yet, other than the fact that I'm considering the case where lambda is greater than 0. Right? I'm restricting myself to that, and I told you that the other two cases has to be disposed of. But now I'm considering, so if I were to consider this, so 1 over RC here would be root lambda minus 1, and this would be minus root lambda minus 1. So I can write it there. So now I can consider 3 cases, lambda equal to 1, less than 1 or greater than 1, right? So, and now I will dispose of 2 of the cases, that when lambda is less than 1 or greater than 1, this is not going to just lead to any finite limit at all. So let's see what happens when lambda is greater than 1. When lambda is greater than 1, right? And I have to see what happens when RC goes to infinity. Lambda is greater than 1, so this is to be 1 over RC times some positive exponent. If the RC goes to infinity, this would vanish simply. So this though, if lambda is greater than 1, this is actually going to infinity, unless of course d1 is 0. That you have to again go further and say that that case is not really possible. But if I consider d1 to be non-zero, certainly this is going to blow up, but I cannot have that case. So I will say that lambda greater than 1 is to be. There is some more thinking you have to do before you finally arrive at it. So I just want to get to the final solution. So now when I look at lambda less than 1, you see that this would be positive because 1 plus root of lambda is less than 1. Yeah, so that minus of this will, what would happen when lambda is it would be 0. d2 term would be 0, then that was 0 even earlier. But now also it would be 0. Okay, lambda less than 1. Both are 0. Yeah. Lambda is less than 1. Both the terms are 0, so the whole thing collapses to 0. Right? So both this is going to 0. And this is also going to 0. So we are having something, the whole factor d1 RC times this plus d2 RC times that as RC goes to infinity for lambda less than 1 simply goes to 0. They are 0 multiplying something, right? Going to be equated to d infinity sin phi. So certainly that cannot happen. It's not heading to the limit 0. In the will be a case for lambda greater than 1, we are seeing that this will go to infinity, whereas again lambda less than 1 will go to 0, right? So we then conclude that both of these cases are to be discarded and arrive at lambda equal to 1. Maybe there's a better way to arrive at this. So nevertheless, now I can write what phi is. If this eigenvalue problem effectively solve d1 RC plus d2 by RC times, well, let's then apply that. Let's apply this condition, right? So as limit RC goes to infinity, right, of d1, so let's having arrived at the fact that lambda has to be 1, right? So then let's take the limit now. d1, d1. That's how you will get d1 times RC power 0, right? Plus d2 by RC squared, and then I have till minus C1 sin phi, right, plus C2 cos phi has to equal B infinity cos phi. Okay, B infinity sin phi here. Sin phi. So from this, as limit RC goes to infinity, this will certainly become 0. So I get minus d1 or d1 times minus c1 sin phi plus c2 cos phi is equal to b infinity sin phi. So from this, if I take cos phi two independent functions, I can easily conclude that minus d1 c1 is b infinity and d1 c2 actually has to be 0. So clearly d1 cannot be 0. So from this I conclude that c2 actually has to be 0. And then d1 c1 is minus. So we have only the group of terms d1 times c1, but you will find that that's all that is necessary to finally construct the solution. So what is now phi 1, right? So phi 1 is d1 plus d2 by RC squared times C1 cos phi, right? Because C2 is 0. And further, we have that C1 d1 is equal to minus b infinity. So that's what I have found. We are still one step away from constructing the potential function. Now I will make use of the other condition on the surface of the cylinder, right? So first I will apply the conditions that limit, and then I discuss this. Limit RC going to R, right? The RC, or rather I can just write it there. The RC times R phi is equal to 0. I now apply that condition. This is part of the no-slip boundary condition. There are two components to the no-slip boundary condition. This is one component, right? And on the surface of the cylinder, the cylinder itself is, we're assuming stationary. BRC is 0. Suppose I apply that, right? So BRC is nothing but minus d phi by drc. So minus d phi by drc evaluated at r has to be 0, which means that if we differentiate, so minus, it doesn't matter. So d phi by drc would be minus 2 d2 by RC cube, right, times C1 cos phi is actually equal to 0. Oh, something is wrong. RC. Yeah, that's true. Phi is lambda equal to 1. So I just put the component that was obtained by differentiating, I just blindly put it there. d2 by RC. Sorry. Yeah, that is true. So that's why something absurd is coming here. Times, this is the F, right? F is this, right? And G was C1 times cos phi. This is what we have. Plus, I also know that C1 D1 is minus B infinity. This is what we have formed so far. I didn't write F, but I probably wrote something that was obtained by differentiating this part for the earlier condition. So this is phi, right? So ERC is minus d phi by ERC at phi, right, is equal to 0 to minus of d phi by ERC. So I have C1 cos phi outside. Then I have a minus, but it's going to be equated to 0. So I have d1 minus d2 by RC square is equal to 0 effectively. Because neither C1 can be 0. Cos phi is 0 at some point, but it's not identically 0, right? So this has to vanish for all values of phi. So I get that d1 is actually equal to d2 by RC square. Right? So when I substitute that, right? So when I substitute that, then I get phi is equal to C1 times, right, D1 RC. D2 is plus D1 by RC. So D2 is D1 times RC square, right? D1 times RC square divided by RC. So that would be D1. D1 RC square by RC. Also very good to be. give me minus sine phi, and then this remains as it is, RC. Which can be written as a form similar to that for VRC as minus V infinity sine phi times 1 plus R over RC squared. So the most striking part of this is the fact that the V phi, the important point to realize is that V phi at R phi is not equal to 0. Okay, so the no slip boundary is actually not satisfied on the surface of the cylinder. This is an important feature of irrotational flow. So what you have to understand is what all we have specified so far. We have considered the velocity profile, right? Taken the flow past the cylinder. We have specified that it is incompressible fluid. We have specified that it is irrotational flow. Other than that, I have not said anything about the nature of the fluid. Whether it's a viscous fluid, it's a linearly viscous fluid, or a perfect fluid, I haven't said. However, what I am observing is that the no slip boundary condition is not satisfied, right? But typically, it is very well known that for a viscous fluid, for a linearly viscous fluid, it has been experimentally sort of verified indirectly that the linearly viscous fluid has to satisfy the no slip boundary condition on a solid surface. But here we are seeing that when we impose a condition of irrotational flow, we are not able to satisfy the no slip boundary condition. So I haven't said anything about the nature of the fluid other than the fact that it is incompressible so far. I have to conclude that an incompressible linearly viscous fluid cannot have or undergo irrotational flow throughout the flow region. Right? We have to put the facts together. So what do we get from here? So I want to summarize what we have learned from this exam, and then we see what it means in some of the problems in the assignment, and also the next topic are related to this feature. So we've seen that for the incompressible fluid, right, plus irrotational flow, we are assuming irrotational flow throughout the flow region. Assuming that the curve of the velocity is 0, so I am saying that the velocity can be expressed as the gradient of a potential throughout, and I am solving for the potential, and I am constructing the velocity profile, and I see that d phi actually is not 0 on the surface of the cylinder. Now you can ask me, what about VRC, how valid that boundary condition is? Now that boundary condition is a very general boundary condition that can be applied to all fluids, and it comes from the fact that rho p dot n is actually equal to 0. That can be applied on the boundary, provided the boundary is impermeable to the fluid, right? So when you have the cylinder and the fluid is coming in, right? So you have the surface of the cylinder, right? On the surface of the cylinder, fluid cannot enter because we have assumed that this is a solid, it is not porous, right? We have to take that. Non-porous, impermeable solid surface, fluid cannot penetrate through that. So what it means is this is the mass flux is 0 because the fluid cannot go through the, this is what is called as a 0 flux condition, right? So the 0 flux condition, since n is equal to ERC here on the surface of the cylinder, this would mean that ERC equal to 0 at RC equal to R. So that is a perfectly valid condition irrespective of what the nature of the fluid is. That's why I clicked only that alone. If I had chosen the other part of the no slip boundary condition, then I would have got something different actually. You can check what you would get. But I deliberately chose this because I sort of knew the answer, and I knew that this is a modified boundary condition. that can be applied. The normal component of the velocity will be 0 when you don't have any fluid doesn't penetrate through the solid surface, if it is impermeable to the fluid. That's a very general condition. So this implies that no slip boundary condition is not satisfied as at the solid surface. So far in all of this, most of the course we have considered the linearly viscous fluid. The perfect fluid was discussed very briefly when discussing the vorticity and the Bernoulli theorem. Right? So, but what we have found, or what has been sort of verified experimentally, especially through the experiments which led to the Hagen-Poiseuille equation, the R⁴ relation for the volumetric flow rate and flow through a pipe, that is obtained through the, so there is no direct verification of the no-slip boundary condition for a linearly viscous fluid at the solid surface. However, since the R⁴ dependence of the volumetric flow rate, which is obtained theoretically, and you can see that that is obtained using the no-slip boundary condition, it matches with the experimental determination of the flow rate versus R. So there is enough experimental evidence to show that an incompressible fluid, linearly viscous, no slip boundary condition at solid surface is actually correct. So correct boundary condition to apply. The only thing I can say from combining these two is the additional assumption of irrotational flow is incompatible with the linearly viscous fluid. So irrotational is related to the vorticity vector being 0. In fact, we will see that it is a solid surface and the no-slip boundary condition that actually generates vorticity at the surface of the solid, and this vorticity sort of diffuses into the fluid. Right? So you have to regard the no-slip boundary condition as an important contributor to the generation of vorticity. The vorticity has to be necessarily generated for a linearly viscous fluid. We'll prove that shortly with an example. Right? So vorticity is generated in any part of the fluid, and then it is diffusing. So certainly in regions at least close to the surface, you can express the vorticity or expect the vorticity to be non-zero. That is clearly incompatible with irrotational flow. Right? So this actually is what led to the development of the boundary layer theory, where you assume that whatever may be the Reynolds number, whenever you have flow past a solid boundary, vorticity has to be there, and irrotational flow cannot be assumed throughout. And so we say that the rotational or the vorticity is restricted to small layer close to the solid surface, where we cannot ignore the vorticity, and then we assume that outside the so-called boundary layer contains the region of non-zero vorticity. Right? Then outside the boundary layer, we can approximate the flow as being essentially irrotational. This is a very simplifying approximation, but it's essential when you're dealing with flow past a solid surface. So it sort of brings in the importance of when you're considering flow of a viscous, anytime, I mean, we have the specific example of linearly viscous fluid, but anytime we have a viscous fluid other than a perfect fluid, right? If you have a viscous fluid, then assumption of irrotationality cannot be justified, especially near the solid surface. So you have to be aware of that. Right? We'll take up this point further, and we start solving the assignment problem, which are all related to some of these ideas in tomorrow's class. Are there any questions?